Okay, so today starts 3-4 factoring polynomials. Recall that if a number is divided by any of its factors, the remainder is going to be 0. Likewise, if we divide a polynomial by any of its factors, the remainder would be 0 as well. That takes us to the remainder theorem. The remainder theorem states that if a polynomial is divided by x minus a, where a would be some real number, the remainder is the value of the function at a. So if x minus a is a factor of p of x, then p of a equals 0. So in order to determine if there's a factor of something, then it means that if we could technically do our long division or our synthetic division, which we'll do a quick review of that. But the remainder theorem says that there's another way to do it. And it's a simpler way. So if we need to figure out whether this is a factor of this longer one, then I could go back to my synthetic division and do -1. Remember to flip the signs and then fill in if we have any blanks, which we don't. So it'd be 1, -3, and 1. And so I bring down my 1 first. -1 times 1 is -1. -3 minus 1 is -4. -1 times -4 gives me +4. And 1 plus 4 is 5. So I end up with the remainder here, which tells me that this is not a factor of that. I can do the same thing here. Start with the -2, and it's 3, 6, 0, because I don't have an x squared, -5, -10. Bring down my 3, -2 times 3 gives me -6. So this becomes a -6. -6 or 6 minus 6 is 0. -2 times 0 is 0. 0 and 0, that's 0. We have -2 times 0 makes this 0. -5 plus 0 is -5. -2 times -5 gives me 10. And -10 plus 10 is 0. I have a remainder of 0, so that tells me that x plus 2 is a factor. So this one was no, because we had a remainder. This one was yes. But we've learned all that in the past. Today, our whole point of learning the remainder theorem is that we can get rid of all of this. It says that if I take -1 from here, we're still switching our sign on it. So this becomes -1, and if I plug it in, I'll find out what my remainder is. So -1 squared minus 3 times -1 plus 1. -1 squared is 1. -3 times -1 gives me 3 plus 1. 1 plus 3 plus 1 is 5. Remember before we found that we had a remainder of 5. That's what came into our little box. So this one would be a no just by plugging in. If I want to find out if x plus 2 is a factor of this thing, I don't have to do synthetic division. Let's just do our remainder theorem. 3 times -2 to the 4th plus 6 times -2 to the 3rd minus 5 times -2 minus 10. -2 to the 4th is 16 positive times 3 is 48. -2 to the 3rd gives me 8. -8. -8 times 6 is -48. -5 times -2 is a +10. And then minus 10. 48 minus 48 is 0. Plus 10 minus 10 gives me a remainder of 0. So just by plugging in, not having to do any division, I can tell whether this is a factor, because it does evenly go into this. So all I need to do is flip this sign and plug it in, and I will find my remainder. Be able to tell whether it's a factor just given that piece. All right, now I want you to try it on these two. Tell me whether it's a factor of each of these. I'm going to start by plugging a -2 in everywhere I see an x. So this is 4 times -2 squared minus 2 times -2 plus 5. -2 squared is 4. 4 times 4 is 16. -2 times -2 is a positive 4 plus 5. That gives me 25. So my answer would be no. Jump down here, flip my sign, becomes a positive 6. 3 times 6 to the 4th minus 6 times 6 to the 3rd plus 6 times 6 squared plus 3 times 6 minus 30. Plus 6 to the 4th is going to give me 1296 times 3 gives me 3,888. And 6 times 6 to the 3rd, well, that's just 6 to the 4th, so this would be 1296. Plus 6 times 6 squared would be 216 plus 18 minus 30. Now before I do anything else, is this going to turn out to be a 0? As soon as I see that this is 3,888, I'm going to have to get close to that being subtracted in order for it to be a factor. So I'm subtracting 1,296. I don't even need to do the math here. And I'm adding two bigger numbers than I'm taking away. So I can tell already that this is going to be a no. Unfortunately for you guys, because there's so much cheating going on, I'm going to make you actually solve it out. So 3888 minus 1296 plus 216 plus 18 minus 30 gives me 2796. So that's a no. So the remainder theorem is pretty simple. All right, example 2 is going to take me into factor by grouping. So factor by grouping is just that. I have 4 terms here. I'm going to group the first 2 together. And then I'm going to group the second 2 together. And I can group this negative with the back terms as well. Okay, so the first thing I need to do is figure out what goes into both x to the 3rd and x squared. Remember, x to the 3rd is x times x times x, and x squared is x times x. Means I can pull 2 x's out because there's 2 x's in each. So I'm going to pull an x squared out. That leaves 1 x in front. And then it doesn't leave anything here, but remember that would be a minus 1 in front of there, so that stays minus 1. If I factor an x squared out, there's still a negative 1 there. Because x squared divided by x squared is 1. I don't think I need to say much else about that. Now let's look at the back half here. What can I pull out of both of these? Now, in general, if I see a negative grouped into with here, I'm going to want to pull a negative out if it's attached to this x. So I'm going to pull a negative out. And then there's a 25 in both of them. So I'm going to pull a 25 out. So then if I pull a negative 25 out, that leaves me with just x. If I pull a negative 25 out of here, it flips the sign and it becomes minus 1. Now you'll notice that these two things are the same, which means that I can technically factor it out or just rewrite it. X minus 1 times, and then the parts that are not inside the parentheses. X squared minus 25. Now, I wish that this was in factored form entirely, but unfortunately it is not. Because we can still factor out x squared minus 25. So I need to know what would multiply to give me negative 25 and add to 0. The reason it needs to be 0 is because there's no x term in the middle here. You could also see this automatically as a difference of two squares. This is a perfect square, and so is this, with no middle term. That tells us that it's going to be x plus 5 and x minus 5. And this is my full factored form. If you didn't understand this part here, you should probably go back and look at the factoring binomials video from the beginning of this chapter. Let's try this one out. So in order to do this one, I group the first two together and then the back two together. What can I pull out of the front? I can pull an x squared out. I had 3 x's. I pulled 2 out. That leaves 1 left. I had 2 x's. I pulled both out. That leaves minus 2. Looking at this back one, I have a negative in front. It tells me I'm going to want to factor a negative out. 9 goes into both of these terms, so that's the number I pull out. If I pulled out a negative 9, I'm left with just x. If I pull out a negative 9, I'm left with negative 2. These two are the same, so they come out in front. X minus 2. And then we group these two together. X squared minus 9. Perfect square, no term in the middle. Tells me that I can recognize this as x minus 2 times x minus 3 and x plus 3. And that's fully factored. Try this one now. Group these together. Here I don't have a negative, so I don't have to worry about pulling anything out. So then we factor out an x squared. We're left with 2x plus 1. Over here, all I can pull out is a 4. So it's going to bring a 4 out in front. And that leaves us with 2x plus 1. Again, these are the same. Pull them out in front. These get grouped together. So this is 2x plus 1. And then this is x squared plus 4. Now, this looks like what we've been doing. They're perfect squares, but this is a positive here and not a minus. Because this is a plus, it's not a difference of 2 squares. So this is as little as we can factor it down to. It will not go any further. All right, well, that's it for today's lesson. Tomorrow we'll pick up here and move forward.